Hello, everyone. This is the second in a series of lectures covering Chapter 18. Today we'll be talking about Section 18.2. There's a particular type of wave superposition called the standing wave that occurs when you have two identical waves traveling in opposite direction along the same medium. And this is something that can happen for transverse and longitudinal waves. So for example, if you make two speakers face each other and they're emitting sound waves with the same frequency and amplitude, then the resulting wave will be a combination of the two, and it'll look like it's not moving. It looks like it's just standing there. The medium's oscillating, but there's no visible motion. So for transverse waves, the way that you would set up a standing wave is to first have two waves, and in this case, to keep things simple, we'll have two transverse sinusoidal waves, same amplitude, same frequency, traveling in opposite directions, and the result is that when they overlap, then we can use the superposition principle, combine their wave functions into one, and we end up with this wave function here at the bottom that you know that now has two different trigonometric functions, one for the kx term and one for the omega t. So what's actually happening, the effect that this achieves having these two waves that are the same, just moving in opposite directions, is that as they move through each other, the interference that they undergo causes the resultant wave to look like it's just moving, oscillating up and down, but it looks like the crests and the troughs are moving up and down, but without any horizontal motion. So here's a breakdown of what's actually happening. The GIF here shows the way to set up a standing wave where you send a wave using a wave oscillator. So you use a machine attached to a string to generate a wave. And on the other end, there's a fixed end, which causes that wave to get reflected. So now there's a reflected wave coming back. But meanwhile, the original wave, the blue wave, keeps getting generated. So you have a continuous stream of this red reflected wave and its original wave, the blue one, going in opposite directions. And so they overlap, and the resulting wave pattern is a standing wave. So you don't see the red and the blue, you just see the resulting pattern here in black. So a few things to point out though is that, right, it looks like the wave pattern is not traveling. The medium's oscillating, right, up and down, but there's no left and right motion like the blue or red waves are doing. So this is why we call it a standing wave, because it looks like it's basically standing in place, oscillating, but not moving. You'll also note a few things about it, that only a few key points throughout the wave actually reach extreme ends, and the further you move away from these points, the less the medium stretches. And then there's some points actually where the medium doesn't seem to displace at all. It's kind of like a fixed stand. So what the question is describing is actually the whole medium undergoing a particular type of harmonic motion. And the formula actually describes simple harmonic motion for any point in the medium. And the terms here, kx and omega t, this is the wave number, this is the angular frequency. This actually are the same as the ones from the two waves that created the standing wave. So whatever the red and blue waves frequency and wavelength are, those carry over to the standing wave. Then you'll note that the amplitude term is not just the original amplitude of each wave, but now it's twice that. But also, there's a sine kx here. So this whole term will actually determine the maximum amplitude of any point in the medium. And What this basically tells you is that different points in the medium will reach different amplitudes, which makes sense because if we go back to this, we see standing wave, only some points in the medium actually displace, all the way to 2a and negative 2a, while other points go a bit less far and some points move at all. So that's what the sine kx does. It checks that, so throughout the medium, there'll be points of max displacement 2a, and then there's points of less all the way to 0 displacement. The term here, the cos omega t, right, you can remember that from the spring block system, the harmonic oscillator. That's just a spring block, right? Your cos omega t is just there to describe how the standing wave oscillates over time. Since over time, right, the standing wave will keep moving up and down. So if we take a still frame of a standing wave here, so you can kind of see one wavelength would be this curve over here, and it's a long exposure shot, so you can kind of see basically the entire path that the standing wave traces. But suppose that initially standing wave is at this position, then over half its period, the standing wave will flip. So this point here of positive amplitude will swing down to negative amplitude, and over here it'll be the opposite. And that's half a cycle. Then to finish the cycle, it'll swing again. So these points that are now at high amplitude will swing back to the original position. The points over here will swing back up. So, like we said, the amplitude of the vertical displacement of any point in the element of the medium depends on its horizontal position, right? Because there's this term here, kx, that accounts for the horizontal position of what point of the medium you're looking at. And the function here, right, is a sine function. So that means that there's some values of x, some points in the medium where this is 0. And if this is 0, that means that this point of the medium is not oscillating at all. There's no displacement. Given that it's a sine function, we can easily determine then what points that would be. And basically, whenever sine, right, is 0 or 180 degrees or 360 degrees and so on, that's when sine function is 0. And if we want to write that then in terms of the location of the medium, the horizontal position in medium x, then we'll have this point of no displacement at the origin 0, halfway through a wavelength, so lambda over 2. We'll have another point of no displacement at the distance equal to the wavelength, then plus a half wavelengths of 3.5 wavelengths. So the general formula for locating this point of no displacement is n lambda over 2. And we call these points where there's no displacement nodes. The way to remember that is that a node is a point of node displacement. On the other hand, though, when is the amplitude of a point in the medium maximized? Well, whenever the sine function is equal to 1 or negative 1, and that's true for 90 degrees, 180 degrees, and so on. So 90 degrees plus pi plus 2 pi plus 3 pi plus 5 pi plus whichever are phases that allow sine to be maximized. So that corresponds then to a position along the medium of a quarter of a wavelength or 3/4 of a wavelength or 5/4. So basically, whenever you are in the medium and your position is equal to an integer number of wavelengths divided by 4, an odd number of wavelengths divided by 4, then you will be at a point of max displacement where the sine term here is maximized. So these points of max displacement is sort of the point where the medium reaches out as much as it possibly can, an amplitude of 2a. And since the nodes are the point of no displacement, the antinodes are these points here along the medium where the maximum displacement is achieved. It's worth also pointing out that in any standing wave, the distance between adjacent antinodes is equal to half a wavelength. So you can actually see that here, right? So the entire length, in this case, the entire length of this picture is one wavelength, right? Here you see one full crest and one full trough. So you can kind of see then how from this antinode to the next one, this is about half the wave. Between nodes, though, also they're half a wave apart, and you can kind of see that how, like, from one node to node, you got to travel half a wave, and between nodes and antinodes, they are a quarter of a wavelength away from each other. Well, neighboring ones are. So this antinode, its nearest node neighbor is a quarter of a wavelength, and this node is a quarter of a wavelength away from the next one, and so on. We're saying, well, you're generating a standing wave, right, with one wave moving to the right and its reflection moving to the left. There's a point in time, say initially, where the antinodes are at their extreme stretch. So some have displaced all the way up, and then two other antinodes are moving all the way down. And as the cycle continues, right, then the medium will oscillate towards the center line at about a quarter of the period, and then the points that were at some point peaks have now swung all the way down and became troughs, and vice versa with the troughs here at time zero. So halfway through the cycle, half the period, the peaks have become troughs and the troughs have become peaks. And then to complete the period, these two peaks will swing back down, these two troughs will swing back up and reach their original position. So you can kind of see that here, right? So one cycle would be, if we start now, quarter of a period, half a period, 3/4 of a period, full period. Do you catch that? So if we start the cycle now, here's half a period, and that's the end of the cycle. So however long it takes for this to swing down and back up, that's one full cycle, which means that the time it takes to swing up and just down, that's half the cycle. Okay, time for a quick quiz. So we got two waves producing a standing wave, and the question is, okay, at the point where the shape of the string here shown with this curve, at this point, what is the instantaneous velocity of all elements along the string? So this is a standing wave, right? And we know that over time, the wave will oscillate like we've shown before, right? All the areas between the nodes will swing up and down, which means that this little crest here will swing down as this trough swings up, and so on. And what can we say about the instantaneous velocity of elements along the string? Well, remember that each element along the string is like a simple harmonic oscillator, and at this point, the peaks are aligned here. The peaks are aligned here, and so are the troughs. So it looks like the standing wave has reached its extremes, which means that it will not, the medium will not displace farther than it is right now. So this is just like a spring when it gets stretched as much as it can. It's going to want to swing back. So at this extreme situation where the standing wave stretched out as much as it can, then it's going to swing back down. And if we look at the GIF here, if we look at this moment where we reach max stretch, we stop and then we swing down, right? So there's a brief moment where we stop, swing down, we stop, swing up, stop, swing down. So that's what's happening. That's the moment we're at. So we swung all the way up, we reached extreme values, and now we are going to go back down. But that means that the velocity of the elements along the string is at this very moment 0, because we're just about to turn around. For this quiz here, we are looking at a point where the waves are overlapping in such a way that they create destructive interference. And the question is, at this point, what's the instantaneous velocity along the string? So This one's tricky because, again, this is a quarter of the way through the period for a cycle of standing wave. Even though there's a brief moment where the line is flat, that's only for a moment. If we go back to the GIF here, and now, do you see that? Again, and now. Notice how there is a point, right, where like all the packets here, all the envelopes are passing through the yellow line at the same time. And that very moment, the line is flat for a split second. But each part of the medium is like a simple harmonic oscillator. So passing through the yellow line is just like a spring block system passing through equilibrium. So this is a point where you have all the kinetic energy is all that you have. There's no potential energy at this point here. So this is your point of max velocity. But note though, right, that like some areas, like this envelope here between node 1 and node 2, this envelope is moving really fast downwards, while this envelope here, when it crosses the yellow line, is moving fast upwards. This one's moving down and up and so on. So there's alternating speeds as they pass the equilibrium line. So the thing is, velocity of elements along the string can be positive or negative. It depends on the position of the element. So, to a question here where we're given two waves traveling in the opposite direction and it produces standing waves. So you have all the required elements here: same amplitude, wave number, angular frequency, but a different velocity, different direction. So just to find the amplitude of the simple harmonic motion of the element of the medium located at x 2.3. So for this question, you can use the simple harmonic motion wave function by taking information from these two functions, right? Because the wave number carries over, the frequency carries over, and now rather than just having the amplitude here, which is 4, is now that will be 8. So you kind of carry that to the standing wave formula and you plug in everything. So for this, the max amplitude of a point at the x position of 2.3, well, you're assuming that for max amplitude, right, this coast term here is maximized, so you're just kind of worried about the envelope term, and what you get is that the max amplitude that reaches is 4.6 centimeters. Now, considering that the maximum possible amplitude that any point on the medium can achieve is 8 centimeters, that's only for the antinodes. This one is clearly not an antinode because it doesn't move up as far. So if we have to find the position of the nodes and antinodes on one end of the string, starting at x is equal to 0. So again, you can kind of use the rule of thumb that we saw to find either nodes or antinodes. Basically, the position of nodes occurs starting from the beginning of the string, starts off with a node, and every half wavelength you get another node. So basically, to summarize that, you say that, well, the position of a node is equal to n lambda over 2. Kind of just tells you, yeah, like every half wavelength you get a node. So the question is, though, well, what's wavelength? And we don't know that off the bat, but we do know the wave number, which does get us the wavelength for the formula. There's a relationship, right, between k and wavelength we can always use. So if we know a lambda, we know k. If we know k, we know a lambda. For finding the position of the antinodes, remember that the antinodes are also have a wavelength away from each consecutive antinode, right? However, the first antinode is the first antinode doesn't start at position 0. At x equals 0, we have the first node. The first antinode happens a quarter wavelength after that node. So the very first one should be a quarter wavelength. That will be the position of the first antinode. And then every half wavelength, we get another antinode, and so on. And the way you can summarize that then is to say that every antinode occurs at n pi over 4 where n is an odd number. So this term just ensures that you start off with n equals 1, the first antinode, and every n after that is effectively half a wavelength from the previous node. And that's all for now. Hope you join me next time for section 18.3. Thank you.